Hello everyone, this is Chinnaiah Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equations with variable questions. So let's get going. Problem: solve x square d square plus xd plus 1 into y equals to log x sine of log x. Given differential equation, x square d square plus xd plus 1 into y equal to log x sine of log x. So we are given a differential equation with variable questions. So we are going to reduce the given differential equation to a differential equation with constant questions by making some substitution. Okay. So here we are given a Cauchy's equation. Now put x equals to e power z, then log x equals to z for x greater than 0, and let theta equals to d by dz. Here theta is a differential operator with independent variable z. Then xd equals to theta and x square d square equals to theta of theta minus 1. Now we are going to reduce this equation to a differential equation with variable questions by making substitution. Okay. We'll replace x square d square by theta into theta minus 1 plus replace xd by theta plus 1 into y equal to replace log x by z, will get z sine z. Then theta into theta, theta square minus theta plus 1 into y equals to z sine z. Right? Then theta square, here minus theta plus theta gets cancelled and you will get theta square plus 1 into y equals to z sine z. So we have reduced the given differential equation with variable questions to a differential equation with constant questions. And also this is in operator form, f of theta into y equals to some function of z. Which is in operator form f of theta into y equal to some function of z, where f of theta equal to theta square plus 1. Now we need to find the general solution of the given equation, which is given by y equals to yc plus yp. Now let's find yc and yp. So we'll find yc using the auxiliary equation. The auxiliary equation is f of m equals to 0, where f of m equals to, we have f of theta, theta square plus 1, right? Let's replace differential operator theta by m, so that we'll get f of m equals to m square plus 1. Then our auxiliary equation becomes m square plus 1 equals to 0, right? Then m square equals to minus 1, then m equals to plus or minus square root of minus 1. We know that square root of minus 1 is I, so we'll get m equals to plus or minus I. Complex conjugate roots, or a pair of complex conjugate. We know that a plus ib is a complex number, then its conjugate is a minus ib. Likewise, a minus ib is a complex number, its conjugate is a plus ib. Right? When m equals to a plus or minus ib, so we call a plus or minus ib as a pair of complex conjugate roots. When m equals to a plus or minus ib, yc will be e power a into z into c1 cos bz plus C2 sine BZ. Okay. In case of A0, we'll get e power 0 into z is e power 0 into C1 cos BZ plus C2 sine BZ. Since e power 0 is 1, so we'll get 1 into C1 cos BZ plus C2 sine BZ, which is equals to C1 cos BZ plus C2 sine BZ, right? Now, when m equals to plus or minus IB, YC will be C1 cos BZ plus C2 sine BZ. Let's write the complementary function of our problem. YC equals to C1 cos, for B equals to 1, we'll get 1 into Z plus C2 sine 1 into Z, which is equals to C1 cos Z plus C2 sine Z. Now we are having YC in terms of Z, we need to write in terms of X, right? So let's replace Z by log X. Then we'll get YC equals to C1 cos of log X plus C2 sine of log X. We got YC. Let's now find YP. Particular integral. We'll find particular integral using 1 by f of theta into q of z. We have f of theta and q of z, right? Where f of theta is theta square plus 1 and q of z is z sine z. We know that e power I theta equals to cos theta plus I sine theta from Euler's formula. Okay. Where cos theta is real part of e power I theta and sine theta is imaginary part of e power I theta. Likewise, e power I into z is equals to cos z plus I sine z, where cos z equals to real part of e power iz and sine z equals to imaginary part of e power iz, right? Now we can write sine z as imaginary part of e power iz. This is equals to 1 by theta square plus 1 into z into, replace sine z by imaginary part of e power iz, right? Which is equals to imaginary part of 1 by theta square plus 1 into z into e power iz. Now, we can write this as series of 1 by f of theta into e power az into v form. We'll shift e power az towards left by replacing theta with theta plus a, and later we'll operate v with 1 by f of theta plus a, right? Now compare e power iz with e power az. Then for a equals to I, we'll find theta plus a, which is equals to theta plus I. Now, shift e power iz towards left, that is beside 1 by theta square plus 1 by replacing theta with theta plus I. yp becomes imaginary part of e power iz into 1 by, we'll replace theta by theta plus I, then we'll get theta plus I whole square plus 1 into z. This is equals to imaginary part of e power iz into 1 by, I expand theta plus I whole square, we'll get theta square plus I square plus 2 theta I plus 1 into z. Then yp becomes imaginary part of e power iz into 1 by theta square. We know that I square is minus 1 plus 2 theta I plus 1 into z. Now, minus 1 and plus 1 gets cancelled. Okay. This equals to imaginary part of e power iz into 1 by theta square plus 2 theta I into z. Series of 1 by some function of theta into z power k form. Now, the denominator is in descending order. Now take the lowest degree term common from the two terms. But in the first term we don't have 2 theta I, right? So let's multiply and divide 2 theta I to this term. Then we'll get right? So that in the next step you can take 2 theta I common from these two terms. Then yp becomes imaginary part of e power iz into 1 by, take 2 theta I common from these two terms, we'll get 2 theta I into theta square by 2 theta I plus 1 into z. This is equals to imaginary part of e power iz into 1 by 2 theta I into, here 1 theta gets cancelled from the numerator and the denominator as well. We'll get theta by 2I plus 1 into z, right? This is equals to imaginary part of e power iz. Now, split this fraction as 1 by 2 theta I into 1 by theta by 2I plus 1 into z. This is equals to imaginary part of e power iz into, now I'll split this as 1 by 2 into 1 by theta into 1 by I into 1 by, I'll write this as 1 plus theta by 2I for my convenience, because it looks like 1 by 1 plus x, so that we can write it as 1 plus x whole inverse. Okay, this is equals to, here 1 by 2 is constant, so I'll take it towards left. I'll get 1 by 2 into imaginary part of e power iz into 1 by theta into 1 by I into, just write this fraction as 1 plus theta by 2I whole inverse into z. Now yp becomes 1 by 2 into imaginary part of e power iz into 1 by I into 1 by theta into 1 plus theta by 2I whole inverse into z. Now we'll use binomial series expansion. 1 plus x whole inverse equals to 1 minus x plus x square minus x cube plus so on, to expand 1 plus theta by 2I whole inverse. Okay, so before expanding 1 plus theta by 2I whole inverse, we'll find the derivatives of z. Theta of z is 1. Theta square of z is 0. See, we can write theta square of z as theta of z. We know that derivative of z with respect to z is 1, right? Or we have the value of theta of z which is 1. And theta of 1, derivative of 1 with respect to z is 0, since 1 is constant. So, theta square of z is 0. Likewise, theta cube of z is 0. And so on. In general, theta for k of z is 0. For k equals to 2, 3 and so on. Right? Keeping this in mind, we'll expand 1 plus theta by 2i whole inverse for x equals to theta by 2i. One plus theta by 2i whole inverse equals to 1 minus theta by 2i plus theta by 2i whole square minus theta by 2i whole cube plus so on. This equals to 1 minus theta by 2i plus theta square by 2i whole square minus theta cube by 2i whole cube plus so on, right? Since we know that the derivatives of z is 0 from theta square, so higher derivatives from theta square, theta cube can be omitted. So we can remove all the terms from here, or we can neglect all the terms from here because it contains higher derivatives theta square, theta cube and so on, right? Now coming to yp, this is equals to 1 by 2 into imaginary part of e power iz into 1 by theta, 1 by I into 1 by theta into expansion of 1 plus theta by 2i is 1 minus theta by 2i plus theta by 2i whole square minus theta by 2i whole cube plus so on into z. This equals to 1 by 2 into imaginary part of e power iz into 1 by I into 1 by theta into 1 minus theta by 2i plus theta square by 2i whole square minus theta cube by 2i whole cube plus so on into z. Since theta bar k of z equals to 0 for k equals to 2, 3, so on. So neglect higher derivatives theta square, theta cube and so on. Okay. So we are going to neglect all the terms from here. Then we'll get 1 by 2 into imaginary part of e power iz into 1 by I into 1 by theta into 1 minus theta by 2i into z. Okay. Then this becomes 1 by 2 into imaginary part of e power iz into 1 by I into 1 by theta into 1 into z. Okay, we can just write it as 1 minus 1 by 2i into theta. We'll write theta by 2i as 1 by 2i into theta into z. This equals to 1 by 2 into imaginary part of e power iz into 1 by I into 1 by theta into 1 into z minus 1 by 2i into theta of z. This equals to 1 by 2 into imaginary part of e power iz into 1 by I into 1 by theta into z minus 1 by 2i into, we have the value of theta of z which is 1, or derivative of z with respect to z is 1, right? This equals to 1 by 2 into imaginary part of e power iz into 1 by theta, 1 by I into 1 by theta into z minus 1 by 2i. We know that 1 by theta is an integral operator. Now replace 1 by theta by integral. Okay, is equals to 1 by 2 into imaginary part of e power iz into 1 by I into integral z dz minus 1 by 2i integral dz. Now this becomes 1 by 2 into imaginary part of e power iz into 1 by I into integral z dz is z square by 2 minus 1 by 2i into integral dz is z, right? Is equals to 1 by 2 into imaginary part of e power iz into 1 by I into z square by 2 minus z by 2y. Right? Now, we are having 1 by I, right? Now multiply and divide I to this 1 by I, will get I by I square. Since I square is minus 1, then we'll get 1 by minus 1. Sorry, I by minus 1, which is minus I, right? Now we can replace 1 by minus I, 1 by I with minus I. We get 1 by 2 into imaginary part of e power iz into, replace 1 by I with minus I into z square by 2 minus 2 by 2y. This is equals to 1 by 2 into imaginary part of e power iz into, now multiply these two terms with minus I. Will get minus I into z square by 2 minus into minus plus I into cancel 2, okay? Sorry, this is z, not 2. Okay. Now we'll get I into z by 2I. Here I gets cancelled. This is equals to 1 by 2 into imaginary part of, we know that e power iz is cos z plus I sin z into minus I into z square by 2 plus z by 2, right? This is equals to 1 by 2 into imaginary part of, so product of these two is cos z into minus I z square by 2 is minus I z square by 2 cos z. Cos z into plus z by 2 is plus z by 2 into cos z, right? Again, plus I sin z into minus I z square by 2 is plus into minus minus I into I square z square by 2 into sin z, plus into plus plus I sin z into z by 2 is I z by 2 sin z. This is I, okay? Now, imaginary part of all these three terms is, okay, firstly we will replace I square by minus 1 in the next step. Minus I into z square by 2 cos z plus z by 2 cos z minus, replace I square by minus 1, will get minus of minus 1 into z square by 2 into sin z plus I into z by 2 sin z, right? Minus into minus 1 is plus. Okay, now pick imaginary part of all these terms. So first term involves I, so this is a imaginary part. So this is equals to imaginary part of all the four terms is minus z square by 2 cos z plus z by 2 sin z, or minus 1 by 2 into z square by 2 cos z plus 1 by 2 into z by 2 into sin z. Okay, this is equals to minus z square by 2 2s are 4 into cos z plus z by 2 2s are 4 sin z. Now we are having yp in terms of z. We need to write in terms of x. So let's replace z by log x. Then we'll get minus log x whole square by 4 cos of log x plus log x by 4 sin of log x, which is our required yp. So we got yp and yc. Let's write the general solution now. The general solution is given by y equals to yc plus yp. Then y equal to c1 cos of log x plus c2 sin of log x plus yp minus log x whole square by 4 into cos of log x plus log x by 4 into sin of log x. This completes the problem. So we have seen a problem from higher order linear differential equations with variable questions in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.